I'll start by saying few words in Italian, then I'll switch back to English for the non-Italian. Ciao a tutti, sono Marco, ci rivediamo virtualmente per un nuovo incontro del meetup del Scala Milano. Grazie a tutti per essere qui. Era un po' che non ci si vedeva, anche virtualmente. Proviamo questa nuova piattaforma, live webinar, vediamo come va, anzi poi magari ci fate sapere, ci fate avere un feedback. Ora torno all'inglese. Welcome everybody to this meetup. And he's pulling my legs, fine. Yeah, I guess we can start. Andy already made us all hungry. Welcome. Today with us we have Leszek from Kansu. Hi, Leszek. He's a backend developer at Kansu, and he will talk to us about Redis streams with ZIO or ZIO. I'm not sure. And he'll be. We have a quick introduction about Redis streams by Tug from Redis Labs. Hi, Tug.
Hello.
So if you guys are ready, I am. Please give it a go. Thank you.
Okay. Remember how I share my screen? I just forgot. We did a test. Well, can you? Don't see. Open share my. Sorry, it was easy. Sorry for that. So I will start with a very quick presentation and quick demo, and then Leszek will do the deep talk about Scala, ZIO, and Redis streams. So quick intro about Redis streams and quick intro about myself. So I am Tug. As you can guess from my accent, I am French, based in France. And most of my life, I work into software vendors company, lately mostly open source, but I spent 9 years at Oracle before. So working on middleware database in different roles between software engineer, product management, developer advocacy. And today I am working at Redis Labs on the developer relation, developer marketing, to help the developer experience the API and communicate about how to use Redis more on project and better. You have some information about how to reach out to me. And also, I continue to develop, trying to contribute to some of the Java client for Redis, JD search, and so on, but also building a personal project. I think the best way to continue to be a software engineer is to have your code in production. So I have small applications on the web, on mobile app, built in mostly Node.js, Redis, and React Native for the application. So let's jump into Redis streams, and so on. So just a quick word. Redis is an in-memory open source database focusing initially on performance and very low latency access to the data. It was built by an Italian, Salvatore Sanfilippo, a Sicilian person. He still lives there. He's still working on this project and many others. It's an open source database developed in C, and you can find information on GitHub on redis.io. And it has been built initially as a simple key value store to access kind of some remote dictionary. So the name is Remote Dictionary Server. But you will see with some of the use case we will show tonight, that is a lot more than a simple key value store. You can build almost any use cases. So, and I'm working from Redis Labs, and Redis Labs is one of the key contributors of the Redis community. It has been founded in 2011 by some engineers that want to build a Redis as a cloud, a Redis on the cloud. to provide a managed service for developers. But in addition to that, in 2015, so not only Salvatore joined the team, but also in addition to have a managed service on Amazon, Azure, Google, it's also you can download it and install an enterprise version that give you an easier scalability, security, and so on, but it's entirely built on the open source. So let's now go into the stream. So one of the important, or one of the view of when you look at Redis, it's a key value store, but the value is made of multiple data structures that you can use depending on the need of your application. So you can use, for example, the very basic one, the strings that you will have behind the key, a simple string up to 512 megabytes. You have bitmaps, you have bitfield, you have hashes that are a set of name value pair behind the key. You may have list, set, sorted set. So you have different data structures that you can use depending on your use case. If you want, for example, to store information about user profile, you may use a hash with many fields about the users. If you want to have a specific way of building a leaderboard, you will use a sorted set with some rich information behind the set to sort data in a specific way. So all these data structures allow you as a developer to choose for a specific use case, for a specific way to interact with the database with specific command to get the most efficient access and the most efficient data structure for your application. On one of them, one of these data structure is a stream. You see that at the bottom right of the slide. And this is what we will be focusing on today. If you go to redis.io, commands, you will see all the commands associated to each of the data structure depending on what you want to do. The important part is keep in mind that you as a developer, as an architect, you can do many different use cases with Redis, for a simple user session store or content caching to fast data ingestion systems or machine learning caching or stream processing. You have almost no limit, especially because as part of the Redis ecosystem, we have a concept of what we call Redis modules that you can add to your database or to your server to add a new data structure or new command. For example, you can index the hashes. So instead of simply query by the key, you can also query by the value. If I go back to the example of using a user profile, you have login, use first name, last name, date of birth, and so on. You will be able to access this information directly by give me all the users that has been born between 1970 and 1980, and the query engine will do that for you. So very open in terms of use cases with a focus on very fast latency, low latency. So let's talk about Redis streams, just to make sure that we are all on the same page when Let's Check Start is installed. So Redis stream is a data structure, and it was introduced in Redis in 5.0 of Redis. We are today in 6.0. It's an append only on read-only data structure. The goal is to you post behind a key that will be your kind of topic. You will post a unique ID based on the timestamp. So automatically you can enter it, or you can let the server generate the unique ID for you. That is a timestamp at the millisecond. And if you try to send on the same topic, on the same key, multiple messages on the same millisecond, the server will increment a number, a counter associated to the timestamp. So you have no limitation in the way you want to ingest the data. And each of the message has a body, and this body is a set of key value pair. And I will show you a quick demonstration after that. And when you want to read the data, so you will add the messages to behind the key on the stream, and you will read the operations in a blocking and non-blocking way, depending on how you want to work with your data. So if we want to look at the overall kind of architecture of an application, on a single stream being the stuff in the middle, you may have multiple producers. So if you are in an IoT application, you may have many sensors sending data, saying this is the sensor number 1 that is located in this specific part of the house, of the factory, sending information about temperature and humidity. And it will send a message from this sensor, so it's one producer from other sensors and so on. And when you want to, when the data is saved, it's saved inside Redis, so will stay forever, at least until you decide to remove the stream or trim the stream. It will be able to then read by many applications. Like Kafka on its message log, it's stored, and then you can after that build new application, new services. In this case, consuming the same messages, consuming the same events, you have two types of application, the blue application and the yellow application. And these two applications will consume in parallel if you want the messages, making that very efficient and very scalable. So you can control how the events come inside the system and when do you want to read the event from where. So you can read the message from the beginning, or you only want to read it from a specific timestamp, or only the new messages for a specific processing, for a specific data logic. And it is persisted. It is highly available and highly scalable. Some of you may have used Redis PubSub and continue to use Redis PubSub. Redis PubSub, it's not persisted. It's a fire and forget information. You send the information to the server. If one or multiple client is here, he will read the messages, but doesn't know if it has been processed properly. Where with Redis streams, each of consumer can say, I am done processing this message. I acknowledge this message has been consumed and processed properly. So to show that, I have just a very basic demonstration based on Redis. So what I use to a part of the demonstration, I use Redis Insight. Redis Insight is a graphic a GUI at the top of Redis. You can connect to any of the Redis you want or you have locally on the cloud, even Elasticache from AWS. And I am connecting to a database where you can see I have no data. I currently have no streams. So I can either post that from the CLI into my graphical tool, but I will use the terminal for this first part of the demo. So the way you post a message is you just say xadd. So xadd is a command to add a message to the stream. The name of the stream, I want the sensor, the timestamp to be calculated by the server. So this will be the ID of my message with the timestamp in the first part. Then I have a set of key values per sensor, T01, temperature 20, humidity 80. Or hydro 80. And now I have other command, like for example, if I want to look at the size of my stream, you see it's one message. If I send another message, you see timestamp change and the number of messages into my streams, it's incrementing. I can look in my Redis Insight, I stream, I can see the message, I can look at some information about the message. I can, if I want, hide some specific field from the value, but that's it. So what I will do now is I want to read the messages. If you want to process these different messages to get information about, for example, to do some real-time analytics, real-time alerts, and so on. So you have different commands. And if you don't know how to work with a specific data structure, you go to redis.io. Here you have all the commands for all the basic commands. So you have 200 commands on Redis, and that's it. And you can choose your data structure. So what I want to look at what I have for streams, and you see I have xadd. And when you click on a specific command, it will give you some information about which one are related most of the time to this specific data structure. So I can read on a specific range and so on. So you will see each of the time the information about the command itself and also kind of the complexity of it, because you want to understand the impact on the latency of your application. So for example, I can say, give me read the 10 last message 10 messages from the beginning starting at this specific timestamp, this specific ID. 00 is the first one. I can, but it's not very interesting in this case, because when you want to deal with an application, you want to be sure my application has processed this message. Nobody else in my specific group of consumer, group of application, a specific service should not process against this message. Or if it fails, I should let it to somebody else to process it. The same way you work, if you are familiar with Kafka, you can use consumer and consumer groups. And if you look at the documentation, you have X group, and you can create groups, you can destroy, you can add a consumer, and so on. So what I will do in this case is I will create two types of consumers to show you the difference between each of them. I won't go into two types of consumer group. I won't go into too much of the detail about all the parameters and so on. It's just to show you the principle. So I'm creating a group that is on the stream named myStream. The name of my group will be consumer group new, because it will read only the new messages. So it's created. And what I will do now, I will read these messages. I will read some messages. And I take another command. I will change the size. And if you see here, the command will be, I read with my group cgnew on this specific stream. So you can have multiple groups, same group reading on multiple streams if you need to. I have a specific consumer that is one for this group. You can have in a group multiple consumers to read in parallel the streams to make it very, very scalable and highly available. I will read 10 messages and I will wait for 1 second. So if I do this, you see it's waiting for 1 second. It doesn't read any message. And I run it again, no new message. If I inject a new message, I will inject a new message. I will inject 2 messages. Since I'm saying this group read only the new event, this is a different parameter, I should be able to see that now I am reading 2 messages. And if I go to my back office, so I can run the command in the CLI, but I can also go here. If I go, I see the consumer group. I have 2 pending messages that has not been read and that need to be acknowledged or processed by the application. I can also, if I want, so in this case, only the new messages has been read, but I can create another application, another service that will read all the messaging from the beginning. Suppose you want to do some Spark processing, to do some machine learning, to create a model. You want to read all the time from the beginning just to compare some different behavior and so on. So I will create another group of consumer, saying this time I want to create my still on the same stream, but I want to read all messages from the beginning. So I do this group. And if I run the command, it will, as expected, it will read from the first message and continue to read until I have, in this case, 8 messages and so on. So in this case, it will continue to read on new messages in the same time now, because this message has been set as already read in the first operation. So your application, as part of the way you work with streams, you have to create a loop, or the API, the framework you use are doing that for you, to call this command on a regular basis. Before going to ZIO and Scala, I will show you 2 examples of dealing with the consumer part is the complex part, or the richest part. Is, for example, if you see here, a very stupid infinite loop in this case, that's the best, but I'm creating a command that reads the group. Each time I have a message, I send an acknowledgement saying I have processed this message. So in this case, it's using simply JS as an API. It's using Lettuce, sorry, I have multiple examples. It's using Lettuce as an API. So waiting for a new message, calling. Or if you use Spring on Spring Data as a Java developer, you just implement the stream listener And the stream listener, every time on a regular basis, will send this and will reset message automatically from the group. And you create the group using the API if you want from the Java side. So yes, so each to answer some of the questions. So on my application, if I go back to the slide, then I will let's check to the presentation. Is I have some producer sending message, and then I have two consumer groups: the blue consumer group, the yellow consumer group. Each block is one consumer. Each of them will keep, I am taking this message, I have read this message, I have processed this message using an acknowledgement. So it's at the group and consumer levels that you control which message has been processed or not. On the pointer, on the specific where I am specifically in terms of processing is stored inside the database, and it's associated to the consumer. So if you look at it now, I should have two consumer group, the pending messages, the last message that has been read. It's because I didn't send the acknowledgement. I should acknowledge to be sure that nobody has sent it. In my CLI, when I run the command, I should have sent an XACK to say this message has been read by this specific consumer. Done for me. Obviously, if you have questions, do not hesitate to post that, and we will collect on. We will answer the question. So let's check. I'm stop sharing my screen. Your turn.
Thank you, Turk, very much for this introduction. So let me share the screen. Okay, so hello everyone. My name is Leszek Gluchowa, and I guess since 2006 I write code. Initially it was C#, then for a couple of years Java, and for the 6 years I am writing 99% Scala. And I have also worked for a couple of years as a consultant for numerous companies. Although the last year, let's say, I work with Kensu as a senior backend data developer. And Kensu as a product is here to understand the analytics area, one platform to rule all the analytics. And nowadays, we use different tools to handle the analytics. Like we have Spark with Scala, we have some Python data processing, we have machine learning with TensorFlow, we have business intelligence with Tableau. And the whole point is to monitor all of those tools at once, because the data monitoring without the context will not give you the right quality. And Kensu is able to collect this information out of those tools to give you the data lineages, the quality information, and model accuracy to allow you to efficiently handle the root cause analysis and avoid the garbage in and garbage out of your tools. What I would like to talk today is briefly about functional programming, as ZIO is a functional library, and what is ZIO and what it gives, and tell you shortly also about the Redis and the streaming part of the Redis, and then we'll take a look into the code on the sample application I have developed, and also later on we'll send you a link to this application so you'll be able to play with this on your own. So why functional programming? And the functional programming has a functional style, has a couple of traits. And one of those I consider very important is the immutability of the data. So we are sure we are able to write predictable code, predictable logic, because no other part of the system application will alter our data and alter our logic. We have functions that are first-class citizens, and that means we are able to assign the functions to variables and pass them around. because we are able to pass them around, we are able to compose them together into bigger logic. We can maintain the referential transparency. And what this means is that if we replace the expression with the result of this expression, with the value, the behavior of the program will not change. And for example, the Scala's future is not referentially transparent because if you assign it to the variable and invoke it a couple of times, basically you will execute it only once. Actually, it will be executed even though you invoke this variable because future is eagerly evaluated. And we have the pure functions that are total. So it means if you have a function from A to B, then it means it can only take A and it can only return B. And actually, the only way to break this contract is to either return null or throw an exception. And by the way, throwing exceptions is simply wrong because it disturbs, it alters the behavior of your program, and you are unable to do much about this. And pure functions are also deterministic. That means that for a given input, you will also get the given output and have no side effects. And we can think about the side effects as anything that makes our functions unpredictable. And given all of that, what we achieve is easy concurrency and parallelism. So take a look quickly on this functional code. We have two simple functions like valid config to make sure that our config is okay, and some logic into the service call method. And there is not much here actually, although there is, I would say, a lot of boilerplate because we use an EitherT monad transformer to define that our program can fail with an AppError or succeed with some A. And we also require our program to provide configuration with the ReaderT monad. So there's a lot to write, a lot of type lifting, and actually so little to do. And I believe there is a better way, or let's say more pragmatic way, to handle such cases, for example. And here with ZIO, basically this code does exactly the same what on the previous slide. And as you can see, this is way more succinct, and we still have those same functions. We obtain the configuration. We return an error side of our program with invalid config, unless valid config returns false. And then we are able to proceed, and we execute our service call and import this function, this impure function, into the ZIO effect. And basically, that's all. We can also a little bit simplify this code if we define that our valid config and service call functions encode already the ZIO effect. And UIO or IO are simply the type aliases for the ZIO. And we can simplify this even more if we encode also this let's say, reader part into the ZIO effect, because this is actually all we have to write to replace the initial code. And this is ZIO that I actually started to be interested a couple of years, 2 years ago. And I am writing production code with ZIO for a couple of months already. And I can, let's say, assure you that I'm not the only one and the only company. And this is already heavily used by the community. You can think of ZIO about a function, like a function that takes some environment R and returns an either of a potential error of the application like E and the success of A. Although the ZIO effect is encoded like this with 3 type parameters. And a couple of words about ZIO. It was, I think, 3 years in the development with over 300 contributors. Among of them was me with a couple of things, although I try to focus more on updating the documentation with more complex examples, for example, that might be very useful for you if you start your journey with ZIO. And recently it established version 1 after like 22 release candidates. It's fast because it's even up to 100 times faster than Scala's future. It's type safe as it allows you to define your requirement, your potential error, and the success of your functions, of your program. It's concurrent as it builds a concurrency on fibers that I will talk more soon. The code looks the same regardless if it's asynchronous or it's not asynchronous, and doesn't leak resources as it allows you to safely acquire and release resources, as well interrupt the fibers you start, and because everything is a function, it's easy to test. Yeah, and as I mentioned, there's already a couple of companies that are using ZIO. I've took those lists from the ZIO GitHub page, and there are many more, and I assume there's way more companies that actually did not put themselves on the ZIO users list. So let's say there is nothing afraid of using this simply because this is relatively young library. And yeah, let's take a look on those precise type definitions. So in this example, we have a ZIO effect that does not require any requirement, any environment, cannot fail, and simply returns a string. Another example is that still we do not require anything. Our effect may fail with a throwable, but please remember, we don't speak here about throwing exceptions. It simply means it may return a throwable type. And in case of a success, we return my data. Of course, we can define our own error ADTs with my AppError like here. And in this example, we require, for example, that we require this effect to provide a user service. And of course, in case we have more requirements, we still are able to safely encode it into the type. And of course, code will not compile until all those requirements are met. As I mentioned, the concurrency in ZIO is based on the fibers. And this is encoded into the, designed into the library. And fibers are a lightweight equivalent of threads. And I think the first implementation was in the Erlang language with the so-called green threads, if I remember. And your application may create hundreds of thousands of threads because, fibers, because multiple fibers can use the same underlying JVM thread. Fibers can be blocked. Fibers can be interrupted. Fibers are automatically supervised because, the application runs on the main fiber, and you are able to fork your effect to run on another fiber, and then this effect may, let's say, fork even more other logic. And all of this is supervised in a way that there is a parent-child relationship. And if you interrupt some of those parents' fibers, then all the child fibers will be interrupted too. And as a bonus point, let's say, in Java 15, there is an experimental support for fibers with the project Loom, although they call them virtual threads. Hopefully, with Java 17, that will have the long-term support. We will have all that running, and libraries like ZIO will be able to make use of it. And ZIO has plenty of combinators and actually ways to encode, to import your code into ZIO environment. And with ZIO Succeed, we are able to import pure functions. With ZIO Fail, we define that our ZIO effect will return the error side of the effect. To import the impure functions, we use ZIO effect. And with effect async, we also get the callback that we can use to execute with either a success or a failure in case we have some legacy code that is based on the callbacks, for example. We have catch sum that allows us to recover on some of the errors of the effects, or catch all of them and do something with this, or return, for example, some success in that case, because we don't care, for example. There's a bracket that allows to safely acquire and release the resources. And this release function will be always called regardless this acquire fate or not. And there is ensuring also that allows us to define a finalizer on an effect. And as long as this effect has started, this finalizer passed to the ensuring will be always executed. And of course, there is a map and flat map to allow data processing and chaining of those ZIO effects. There is a ZIO fork that I mentioned that is used to ask the effect to execute on another fiber. And for example, there is also ZIO raise that allows you to raise two effects between each other, given the maximum time you pass. And if one of those effects completes first, then the other one will be safely interrupted. There is repeat and retry that take a schedule. This is another data structure from ZIO. It allows you to define the recurrent schedules for the repetition and the retry strategies in case your effect returns an error. And of course, there's way more to use. With ZIO, we also get multiple data structures, and I will here mention just a couple of them that are used in my sample application. There's a promise with an error E and success A that may be completed only once. There is a ref that allows us to handle concurrently mutable data. There is chunk that is basically a sequence data structure, although backed by an array. That is usually, so far I know, faster than Scala's vector, and non-empty chunk that allows us to define the data structure, the sequence that will always contain at least one element. There's a schedule that I mentioned that is that we can pass to retry and repeat combinators that allow us to define the recurrences of an effects. And there's the stream that we will, of course, talk more today about. That, as you can see in the type definition of the stream, we have REA. The R, like with ZIO effect, describes the requirement. The E describes the error, and the A describes the element that is produced by the stream. And the streams are consumed by sinks. That is, I see, and sound a little bit more complicated, but it all makes sense. Again, we have the R that takes the environment, and an E that describes an error. A means the element that are consumed by the sink. B means the success result of the sink, and L is the leftover. Okay, so those are the data structures that I have used in my simple application. Okay, so there are a couple of ways we can construct this stream. There is an apply that allows us to pass directly the arguments from the variable that allows us to construct the stream out of the sequence. And from effect, like from the ZIO effect that I have used, for example, in my application. From chunk, like from the another sequence, let's say, but from this chunk data structure coming from ZIO, and from the queue. So, for example, we can have a queue that we push the elements into, and then they are processed by the stream. Of course, we have to somehow process the information in the stream. So we have the map that takes simply a function. We have map m that gives us the stream element and requires to return a ZIO effect, and flat map that also gives us the stream element and requires us to return as a stream. There are parallel counterparts of those mapping functions. And by the way, I think I forgot to mention is that ZIO, of course, has also the ability to handle the mapping functions in parallel. There is ZStream transduce that takes a ZStransducer that is a stream processing function that allows to aggregate the elements, map them, process them the way you want, and decide whether you would like to push or emit the element further or not.
There is a ZStream throttle that allows to slow down the stream. Grouped, that takes an input, the amount of the size of the elements you would like to group, and grouped within, that allows you to also group the elements, but in the given time. And if this time passes, you will simply get what the stream was able to group within this time. And like with ZIO, we have also repeat and retry that takes a scheduled data structure to define the recurrences. And of course, there is way more. One very important aspect of streaming is that we can, there is a so-called pipelining. In the first example, when you see the ZIO with map par for comprehension, is that we have some input data and a process function, and we want ZIO to process those input data in parallel within 5 fibers. And then we take the result, and then we again process those results into 10 fibers with process even more function. And the problem here is that this process even more function will not start until all the processing of the first line will finish. And this is different than in the stream, because if we write the same into the stream, where we process in parallel the process function and process even more functions, the process even more function will start as soon as the first execution, as the first fiber of the process function will finish, will emit some elements. So this is, more efficient to handle the data processing. And here we come into the Redis part, although I guess I will go quickly on that, as Tug already said a lot. We use Redis as usual, as many of us, let's say, for the very fast cache with the key value storage. But Redis has way more than that with the Redis data structures. And we at some point decided that we have to process the data in a streaming fashion. And we maintain mainly the on-premise installations. That gives us some constraints and requires us to handle the technology in easy way, to maintain some easy deployments, easy maintenance, easy recovery and failover strategies. And Redis gives us that. And because we already used Redis, we were able to use more out of it. And I guess the same will be in your cases, in your companies. Redis is in memory, but commands can be persisted, and Redis gives you the possibility to decide how often you would like those commands to persist. And of course, it will affect the speed, but it gives you the possibility to decide the accuracy, or how much you would like to be sure that you do not lose any information. Because its memory is fast, as I mentioned, it gives us easy deployments, maintenance, and recovery. And we can use Redis for numerous things because it's built on it defines multiple data structures like stream. Redis can be replicated, and Redis can be sharded, clustered. Although it's worth to mention that in terms of the streams, you cannot put the same stream on multiple nodes because the single stream must be on a single node. Although there is, let's say, not out-of-the-box possibility to handle this case, as you can have some, for example, suffix on your stream name, and decide on which stream you would like to send data when you produce them. Redis also has numerous modules like Redis Search, Redis JSON, Redis Graph, so you can still enhance Redis for your needs. And like Tug mentioned, Redis also supports PubSub with this fire and forget approach. And of course, those events will be consumed only by those clients that are currently alive. Dirk also mentioned how this stream is structured, but maybe I will just clarify or mention again that when we have a stream, the message consists of, let's say, header and the payload. The header is this this message ID that consists of a timestamp of the creation within the stream. And in case we have two events that are being ingested into the same exact moment, then we have this suffix like -0, -1 that allows us to order the events within the stream. And then we provide in the payload, we provide a list of key value pairs of our data. And in a stream, we may have those multiple producers that are running in parallel, and we may have multiple consumer groups, independent consumer groups that consume the stream in parallel. And also, like to mention, the communication with Redis is based on comments. And given that we have some consumer group A, we may have multiple consumers there. And when consumer reads the message out of the stream, this message is assigned directly to this consumer. And in case, right after this message is read, and you may, for example, spend, I don't know, a minute processing this message. After this message is read, is being set as a pending message, and will be assigned to this consumer all the time. Although we have the possibility to claim this message out of this consumer to another consumer in case, for example, this consumer is down for too long. Tug also have shown you a couple of methods, comments, that we can use to handle the communication with ReaderT, so I will not go into the details for this. And I can also tell you that initially I started with one. There are numerous SDKs for it, including those for Scala ones. And actually, this is the first one I started when we have dealt with the key values approach of Redis. But this Scala library lacked support for streams. That's why I decided to take a look on the officially suggested SDKs from Java. And I found Redis that is, I believe, widely popular, and it seems it handles all the possible cases. So in case you would like to go beyond key value storage or streams, you will be still able to use the same library for your needs. I know also that there is a ZIO Redis in the making, although there is no ETA for this library. I don't know how far they are right now and when they will finish. I know that this will not be some wrapper around any other Java library. They will communicate with Redis directly. Later on, I will also send you the links to the resources and, of course, to the sample application. So you can play with on your own and maybe start with either Redis streams or with ZIO. Okay, so yeah, let's take a look on the code. I see there are no other questions. I hope you see the screen clearly. If I should even more increase the font, please let me know. Okay. So please for now focus on this piece of code. This is our stream. So basically what we have to do is execute an effect to read the messages. Because we may read multiple messages like ND, not some line text, is IntelliJ. And because we may read, for example, 10 messages out of the stream, we need to flatten the sequence into one message of the stream. Then we have the event processor of this message. Then we are able to acknowledge this message. So basically, on the high level, that's all. Although because this communication with Redis is command-based, we have to keep repeating this logic. That's why we have this repeat combinator here with the defined repeat strategy. And I understand that by default, of course, we would like to repeat this logic forever. And when we shut down the application, we can pass the shutdown hook. So we tell the stream that it should not process any more messages. Okay, so let's take a look into the details. I try to make it like a real project. So you have some logs and also, you know, not only the happy part handled. And simply, sorry. And as I mentioned, when you read the Redis stream, even though you may still be in progress of processing this message, of course, on the Redis side, this message is marked as a pending. So we cannot have, I mean, we also, at some point, we have to do something with those pending messages, because if we do not acknowledge this message, it becomes pending all the time. But at some point, eventually, I would like, of course, to handle this message. One of the approaches we could take, for example, is that we have we have single stream, and we have one process that within the consumer that handles those new messages, and the other process within the same consumer that handles the pending messages too. But we cannot do this, as in this case we may handle the same message twice. So what we have to do is that actually is that we have to keep reading, let's say, those new messages, but at least from time to time, we have to check if there are any pending messages to read. And we can either do this from, in case our stream has failed, or simply from time to time. And in my example, I have decided to use this from time to time, and this is based on the configuration. For example, you can define that the pending messages will be executed, will be read every 1 hour. But to do so, I had to define the stream state. And to do this, I have used this ref data structure. And the stream state decides for me when was the last time I consumed the pending messages, if I should asking for the pending messages, and what are the messages I have already checked in case of the pending. And the reason for this is that imagine that for 1 hour we consumed the new messages and we were unable to acknowledge some of them. After 1 hour, we read the pending messages, like here we have the 10 messages, and we try to process them again. Actually, they may fail for numerous reasons. And even though we try again to process them after reading the pending messages, we may again fail, and we don't, of course, don't want to consume those pending messages all the time, the same messages all the time. So I'm making sure that I'm keeping track of those Redis message IDs, and I do not process those that I have already read. Other than that, I simply keep reading those new messages. And you can see that this get events method returns a ZIO function. Because this is a ZIO function, I have to import it into this ZStream from effect, and it returns a chunk of read results from the stream. That's why I have to flatten those chunks, and then I pass those events to the event processor. What I could do here is that the event processor could be simply a function from some argument, from some input into the ZIO effect. But because of this pipelining I have mentioned to you, I decided to put here another function that will give the stream, and it requires you to return another stream because it gives more possibilities. And then I pass this stream processing into the whole stream. The stream, the event processor, has to return an option of stream message ID. The reason is that this event processor may be complex. Okay, maybe it will do some little thing with this, but on the other hand, what it can do is, like in our cases, connect to other microservices, gather some information, do some heavy processing that may take tens of seconds, for example. And there is, even though you can retry each of those little steps, at some point you have to eventually pass and try to process the other message. And in case you decide that your stream cannot proceed anymore with this message, this event processor may return none. And with none, I check that I should not acknowledge, of course, this message, because there will be nothing to acknowledge, and I simply move on. So this message on the Redis side will be kept as will be kept in the pending state. If I have the message, I simply acknowledge it. And I understand here we have a couple of types, generic types here, but the reason is that I wanted to build a generic code that allows me to build numerous streams processors within the same application. The R type here is the environment that could be provided with the event processor, right? Because the event processor may depend on other dedicated services needed to handle this message. The A is, of course, the data type that we process. This part is actually a fancy thing I have decided to build because I wanted to define on a compile time level the stream. And here I wanted to define on a compile time level numerous streams. And the configuration is that I will have some generic configuration with the group name, consumer name, different repeat strategies, and so on and so on. But this is just the basic one, because for dedicated streams, I will have to somehow provide through the configuration the keys I have in my payloads of the messages. So let's take a look on the example on the sample stream. Here is the notification stream. So I defined my input that takes some clock that is needed for the retry and repeat strategies, the logging service, my dedicated configuration, and the Redis stream for a given, the Redis stream logic for a given stream, that is notifications. Here I provide also this shutdown hook. Of course, this there will be a single shutdown hook triggered by the application shutdown that is passed to numerous streams. And there is my event processor. Of course, this is a simple one, but I parse the raw data into my dedicated data type. That is a notification added event. In case I do not support something, I have the incorrect event. Of course, I flatten the chunks, and I process this event in parallel. What I have here also for the event processor is that, okay, let's say there is some additional work to be handled for this event, but this additional work may fail, of course, for numerous reasons, and some of the errors can be retried and some cannot. So in my real project, let's say, I have the logic that distinguishes those cases, and in case I have a retriable error, I return a none of this event stream, so I will not pass the stream message ID, and this message will not be acknowledged. Otherwise, in case of some serious error that it doesn't make sense simply to retry, I return this stream message ID, so this message will be acknowledged. And of course, what you can do is either to put some dedicated information into the log, or even produce this problematic event into some other stream. And let me show you how it is set up. So I have a sample consumer that is providing the shutdown hook, starting the notification stream, and in case of the application shutdown, it handles the shutdown in a way that I complete the shutdown hook, I wait, and then I wait for the stream to safely shut down its processing too. Of course, up to 5 seconds, because I don't want the application to hang. Okay, maybe just a couple of words here, because what we have here is this let's say dependency injection, the definition of the requirements onto our effects or the streaming, and this is built in using the Z layer encoding. That is basically like runtime time composable dependency injection in ZIO that honestly deserves some additional presentation, so I will not go into the details right now. Here is this definition of the notification stream. You can also see that I have something like the stream collector. The reason is that we imagine that you have a consumer group with multiple consumers. And those consumers, let's say, run on multiple nodes. And as I mentioned, when given consumer reads the message, it is assigned into this consumer. And imagine your consumer, after a couple of days, your consumer is shut down. You don't want to lose those messages. You want to process them eventually. So what I have here is some additional code that is, for example, executed every 1 hour. And what it does is that it uses expanding command to collect the information about the available streams in our consumer group and their state. And for example, how many times there were read attempts of a given message, or how long the message is being idle. That means it was not read for a given time. And given this information, there is additional logic that allows me to either, for example, acknowledge message that was being read 50 or 100 times without success. Or if I see that the message was not read for 20 hours by the consumer, that means most likely it seems the message that this consumer is down, and I have to claim with the claim command this message from this consumer into mine. I have also a producer here. Give me a second. Here, and producer is simple. What it has is that it simply takes the given stream and allows to produce a message for a given key with, of course, given value. And basically that's all here. Of course, I have some additional retry strategy, repeat policy. And okay, let's go for a second to this Redis stream, because you have seen that basically all those execution of those Redis stream commands were basically one-liners, and the reason, even though I have used Java SDK, and the reason for this is I have some sort of proxy class, service class to handle those cases. Let's take a look here, for example, when there is the execution of the read command. So I have the Redis stream instance, the Redis stream basically, instance for a given stream name. And I can use this Redis stream to, for example, execute the xread group message asynchronously. And what I have to do is to encode, to import this logic into the ZIO. And I can do this with, for example, task from completion stage. The task is a type alias for ZIO that has a throwable as an error return type. There's also, ZIO has also a combinator called effect blocking that allows you to execute your logic on a separated thread pool, the blocking thread pool. I have not used it here because it wouldn't have actually any effect, because I've checked in the source code of Redis that under the hood, it maintains its own features and threads. So what I can simply do is to handle this asynchronous computation into the ZIO effect. And basically what I have in all those cases here is that I translate from Java types into the Scala or dedicated ZIO data structures. And it works like this. I have also, I guess it's very late, and just to let you know, I have also tests for this using the ZIO test library that handle all those cases, but I guess we are running out of time, so it doesn't make sense to just go into the details here. Then maybe the last thing I can show you is that we can execute the producer that is producing a message, random alphanumeric string every 5 seconds, about 5 seconds. And we can also run the consumer that is consuming those messages as they come. With, of course, some additional debug and info and warning and error logs to have it like a real normal, let's say, production grade application. And I can also show you, like with Tug did, that with Redis Insight, you can go, you can take a look on the Redis itself and see what is actually happening. And also with the streams, as you can see, those streams are being processed, being produced, and are being consumed. And we can clearly see here what is happening. Okay, and I guess that would be it. I hope you like it. I mean, if you have any questions, I will try to take a look on them now.
Thank you, Leszek. Very interesting.
Yeah.
I collected two questions. Let me see. One was okay. Yeah, actually, Gabriele replied, but the question was: do the error ADT have to extend throwable or exception?
It's up to you. It's just the type definition, right? So needed the throwable will be the lowest one, let's say. And I have decided here to use the throwable because the Scala, sorry, the Java SDK library basically is able to give it me that. Although when I have this encoding, this import of the Java code into the Scala one, into the ZIO one, I can also map the error and use my own error ADT. I don't have to use the throwable. I can use anything else I want.
Right. The second question I collected was: when you power map the events, how is the actual fiber/pool selected?
With the power, so I know. I mean, there is the main thread pool handled by the ZIO itself. So when you power map, you simply use this thread pool. That's why in case you have some IO operations, you need to encode them into the blocking effect. Otherwise, you may, at some point, you may simply reach a deadlock. But you also, there's a combinator called execute on. And you can also define your own thread pools, and you can pass this execution context into the effect. And this way, the effect will be executed on your dedicated execution context. And after the execution, it will go back to the main one.
Makes sense. Hope the Ivano who asked this is happy. I have a more general question about ZIO. How are you enjoying your time using ZIO? I haven't found the time to play with it myself, but it looks very interesting.
I started with ZIO, I think 2 years ago. And let's say my first take was on initially ZIO didn't have those three types. It was only a bifunctor that allow you to define an error and a success case. And even though, for example, I used a lot Monix with the task data type, I always had to wrap all my application logic into the either. That actually led me to EitherT mono transformer because it was then simpler to use in case, for example, of the for comprehensions. So I was very happy when John DeGauss actually revealed that he's building the effect that will allow me to encode the error immediately, because I was doing this anyway. Fortunately, it turned out that we are able to encode a little bit more into the ZIO, like with this reader, basically, transformer. So it's like encoded into the ZIO itself. And I understand, of course, it doesn't handle all the cases, but we can, I believe, say that it handles the majority of the cases, right? The error type, separated error type, and the reader effect, reader part of our effects. But for now, it has, of course, way more to do. It's fast. And without those reader and either transformers, we, of course, save some time and resources, as we don't have to unwrap all those effects each time we do a flat map.
Nice. Good. Let's see if there are more questions. Guys, don't be shy. Otherwise, I think it's about time. Looks like everybody's happy or leaving.
Yeah, it's quite
it's dinner time here. Yeah, so. Okay, thank you very much.
Thank you very much too.
Thanks also to Doug for the introduction. Thanks, Kensu, for making this happen. And hopefully see you around.
Yeah, see you next time, hopefully. Have a good night. Bye.